I'm Ted, and I've been working on the WebAssembly port along with Ismail, and it's still in alpha, but we have a lot of functionality working. We think it'll be very helpful to people trying to use this library from JavaScript. So what we're going to be going over is introducing what the JavaScript/WebAssembly port is, what it does do, what it doesn't do, what it does fast, what it does slow. Going over an example of using fully homomorphic encryption within the browser, which replicates a simple integers example shown in previous webinars, reviewing the performance of it just in more detail, going over examples that run within NodeJS. So this would be something you run on the command line, maybe on the back end, maybe just as a script standalone, that go over threshold FHE capabilities, proxy re-encryption, buffer-based serialization, and also what we're going to do to the WebAssembly port in the future. So we have an alpha release of the WebAssembly port live right now, and you can find it at that link, just GitLab PALISADE WASM. We are currently developing an npm package, so then you could just do like npm install PALISADE crypto. You would have access to everything. Currently, you have to build from source, but that will very soon be fixed. We're still in alpha, so the API is subject to change. PALISADE, the WebAssembly port, is currently optimized for BGVRNS, CKKS, and FHEW, which should cover your needs for integer calculations, real number calculations, and Boolean circuits. If you choose one of the schemes that has not been optimized, it may be a little slower, such as BFVRNS. And the WebAssembly environment is typically limited to 4 GB of RAM on the browser, so that may influence which kind of applications can be ported to the system. So in terms of writing code for this port, the bindings are written such that they closely follow the C++ functions. So as you can see here, we have the JavaScript file on the left and the C++ file on the right. And other than just the syntax of JavaScript versus C++, the naming of everything and the way that you store objects is largely the same. However, there are a couple key differences that I'll go over in more detail later. So all of the examples shown in the previous PALISADE webinars are supported by the WebAssembly port. So that includes the Boolean circuit example, including serialization, and all of the integer examples with serialization again on that side too. Real numbers, threshold, fully homomorphic encryption, and a proxy re-encryption example. And of course, all of the structures used in the proxy re-encryption can also be serialized, which kind of enables a lot of networked applications. So in terms of naming, there are some naming conventions in C++ that just don't translate quite to JavaScript. For example, templates don't exist because they're a compile time structure. So for these special cases, the namings have been changed, but as you can see, it's pretty self-explanatory. And some of the methods like eval_mult, which have a bunch of overloads. For example, you could eval_mult a ciphertext and a constant. You could eval_mult a ciphertext and a plain text, or you could eval_mult a ciphertext and a ciphertext. And so just to keep it very clear what you're doing, we have split these up into distinct methods for the JavaScript bindings. Additionally, enums are going to be in their own namespaces just due to the way that importing works in JavaScript. So as previously described, WebAssembly users, being people who are using JavaScript or TypeScript, which then loads WebAssembly, can use PALISADE to perform homomorphic computations over Boolean circuits, integers, and real numbers. And we have a scheme optimized for each of those use cases. And we have serialization functionality that works with in-memory buffers. And the reason that we don't have direct file serialization in the WebAssembly port at the moment is that WebAssembly has you have to mount a virtual file system to get that working. So we thought it would be simpler just to give the user a buffer and let them save or load from whatever file they want externally. So, and here we can see an example of the browser application, which showcases the simple integers example described in a previous PALISADE webinar. So as you can see, all of the crypto context parameters can be set at runtime, as well as the values of the plain text. And at the click of a button, we can run the homomorphic operations, which experiences about a 5 times slowdown if you choose a correct scheme. And that performance impact will be discussed later. So in terms of the actual code that's required to make a demo like this, obviously, if you're making a web application, you have to write some code to interact with just like the HTML, but that's fairly simple and doesn't have any implications for your homomorphic operations. In terms of the actual FHE operations, again, you can write it very similar to C++, but there are a couple of key considerations that need to be made. For example, JavaScript does not have compile time type checking, so these coercions must be made manually, or else you'll face an error at runtime. But that's not too big a deal, and generally you realize what's wrong pretty fast. The larger issue is that JavaScript does not keep track, or has no way to tell you that a handle is going out of scope, so you must delete all of the C++ handles manually, or else the application will face a memory leak and inevitably crash. So one of the simplest ways to solve this is to simply keep a list of all the handles that you have generated in whatever context. Maybe it's within a function, maybe it's within a class. And every time you generate something from C++, just add it to that list. And then make sure that you delete these handles such that you can run your application and keep going, and keep the memory size the same. So all in all, that example only took under 200 lines of code to use fully homomorphic encryption within a web browser. So the WebAssembly port will also feature TypeScript bindings, which can catch errors at compile time rather than runtime, and provide accurate autocomplete, which should speed development of these applications which use homomorphic encryption. And by introducing TypeScript, you get many of the structural guarantees that C++ provides, like knowing that this variable is this type, and you can guarantee that and not just guess at it, while also maintaining the flexibility of JavaScript's object-oriented and functional patterns. So for example, you could perform a map or a filter over ciphertexts, and that'll all work out of the box. In terms of documentation, we have some documentation for the internals of this library up at the moment, which just describes how we're binding the things together. And soon we will have documentation that accurately represents the TypeScript bindings and tells you exactly what each function does. And within that documentation, we'll also be linking back to the original PALISADE documentation. So for example, eval-mult cipher will tell you, if you want to learn more about this, just look at the eval-mult in the C++ side. Are there any questions about that part?
Yes, so there was one question, but I've already answered it, Ted. So about the YouTube link, I believe, for this recording, for this talk. So I mentioned that this will be uploaded to YouTube and shared just like the previous webinars. Mm-hmm.
All right, sounds good. I'll continue then.
Thank you, Ted.
All right, so sorry, this is Ismail's part, right? Do you want to share the screen, or should I keep going?
Oh, yes. Let me share the screen. All right. So, hi. This is Ismail. I've been working in safety critical embedded software for last almost 12 years, and I've also worked in blockchain technology, and then I was introduced to this state-of-the-art PALISADE, and actually I have been working in the WSM port. Talking about the performance, the GCC and Clang has a little bit difference. Clang is somewhat 2x, 3x slower than the GCC native executions. So that is already been covered in the original PALISADE library. So when we are comparing it with the NodeJS build, for example, we have used libbenchmark as a standard to compare the performance. So in the right hand side, you can see the just this is image of performance benchmarks using Clang, and now in upcoming slides, I'm going to demonstrate or just describe that if we compare the WSM with native GCC, how it performs. So we have chosen three schemes: BFVRNS that is not yet optimized, and CKKS and BGVRNS. So they look similar, somewhat 5x slower.
So Ismail, may I interrupt you for a second?
Mm-hmm.
Just for my understanding, as far as I know, when we go from a native binaries, let's say, to WebAssembly, there's typically like a 2x slowdown, right? Just regardless of what computations are performed. And in this case, I think Palisade also uses 64-bit operations, which are emulated, right? Just if you could briefly explain, I mean, I think it would help. Mm-hmm.
All right, so definitely there is a generally there is a 2x slowdown. Palisade definitely uses 64-bit computations, and in WebAssembly that are not fully supported in some way, and that is the reason of the slowdown. But if we compare it to the Clang, so as the WebAssembly is Clang based, so the performance is almost comparable. So we can say just a equivalent or 1.5x slowdown in case of WebAssembly when we compare it with the Clang. So these performance comparisons are with the GCC. So for specific operations, for example, this shows the keygen operation. So when we perform a keygen with BFVRNS, CKKS, and BGVRNS, we see the slowdown of almost 5x. And then this is a encryption operation. So this is also almost 5x slowdown in all the schemes. And this is decryption. This is also almost same, exactly 5x, and some cases more than 5x, especially for BFVRNS. And then this is add operation, so similar situation. But when we look at relinearization, so CKKS and BGVRNS are actually almost 5x or 6x. And the BFVRNS that is not yet optimized for mult or rotation operation. So this is its slowdown is way larger than the other schemes. So in general, or in summary, we can say that for integer calculations, BGVRN is the preferred scheme, and for real numbers, definitely CKKS has been used. So both of these schemes are optimized for WebAssembly as well, but multiplying and rotation of ciphertext suffers approximately 5x slowdown with BGVRNS, but receives a huge 20x slowdown with BFVRNS. So we have a couple of examples that we are going to run.
Yes. So Ismail, while you're setting up the examples, just maybe I'll add a high-level comment. Since BGVRNS and BFV, so BGV and BFV work with the same plain text algebra, which basically they're used for integer computations. If one uses WebAssembly, our recommendation is to use BGV because it's faster and it has been optimized for WebAssembly. So this is, but CKKS certainly should be used for any real number computations, and FHW for Boolean circuits. So that's just wanted to highlight that we have not yet optimized BFV. Mm-hmm.
All right. So here's the example. As you guys have already seen the code, they look similar. Left side is the JS pre-buffer example that uses the proxy encryption, and the right hand side is the C++ example. So they look almost same. So that's the way of access is a little bit different, but you can use everything as we have been using in Palisade. So I'm going to run both side by side each example. So threshold FHE. So there would be we would so this is threshold FH in JS. So I want to demonstrate that they actually look exactly the same when we run them. So the extra slowdown for the time being is due to the bindings. So when we run them dynamically linked, so they would be much faster. But for the time being, the slowdown is due to the binding. But if you, so I have threshold fetchy, and this is also. So if I then look at another example, simple integer serialization example. So this is how it looks on the JS, and this is how it looks on the Palisade. So the text and strings are supported exactly the same as they are supported in the native implementation. So next we have a pre-buffer example. So then we have a pre-buffer example here as well. So all the examples have been ported, and they can be used directly from command line if you're using Node. And so these were the examples. And for next, we have a considerations for future work. So we what we have been planning for that. So actually, there are, what are the benefits that we could get from a WebAssembly port? So first of all, definitely, and obvious one is that develop web-based homomorphic encryption applications with comparable performance when compared to native execution. And there are definitely many limitations when using this. And currently, generation of crypto context supports a limited number of parameters. So as we have not yet ported all the crypto context generation with all the parameters, currently we support a limited number of parameters in alpha release, but we are planning to extend that. And the next limitation is that the already discussed by Ted, that anything we create, for example, if we generate a crypto context, we need to delete it. The way we use dynamic allocation in the C++, that is somewhat similar in the JS as well. So OpenMP is not available for WebAssembly yet. So that feature is not usable. This is also a reason of slowdown. So very limited SIMD support, mostly through emulation, and only the 128-bit wide instruction for AVX instruction set are available. 256-bit wide AVX instruction are not provided. So this is also a limitation to that. What are the alternatives for Palisade WASM? Other bindings options are also available where users can write their own some bindings. For example, C++ add-ons are available where you can perform native API or simply dynamically link the C++ code from with JavaJS. And so future work. So what we have considered for the future work is that optimize other schemes for WebAssembly as well. So, and potential support for multi-threading by WebAssembly. So there are some ways that, for example, the initial way is pthread, but there are other ways to support multi-threading in WebAssembly as well. So there might be some potential work in the future in this direction. So examples, so we are looking forward to implement some example to highlight potential use cases of Palisade WASM for example, develop web-based homomorphic solution, networked threshold FHE proxy encryption examples, so that interested parties can see them and utilize them. And definitely would love more contributors. At least please try to use Palisade WebAssembly as it is right now to help us improve it, so that there is any mistakes or some things you find would be improved. Please test it and let us know. And please help us spread the word. Thank you very much. If you have any questions.
Yes, so there is one question that I see. Is there any compiler like Microsoft EVA? I guess this is not a question specific to WebAssembly, but more of a question on the compiler automatic compilation capability for Palisade. So I'll probably take that question. And Kurt, if you want to add any comments, yeah, feel free to do that. So we did, I mean, basically, there's some work that we've done on building compilers. And for instance, there is an earlier work, Rampart, that we previously described, and I think we even mentioned in one of the webinars. So that compiler is not publicly available at this time, and we're basically putting more effort into building compilers, but there is no publicly available version that exists. In parallel with this effort, we have been improving the API and usability of all schemes. So trying to essentially incorporate some of the features that typically a compiler would do in Palisade automatically, such as for approximate homomorphic encryption. So in the previous webinar, we discussed that many of the usability issues related to rescaling and related to basically that make using the CKKS scheme hard. We automated everything that's related to that, and also reduce the precision there. So basically there are two angles. So one is improving Palisade, the other is building compilers for further capabilities on top of Palisade. And we're certainly working in both directions. And Kurt, I don't know if you want to add any further comments on this or.
Yeah, happy to say a few words. I mean, this whole notion of compilers has been a very strong research area that's gotten prominence in the last few years. As was shared, we had some of the Rampart's work. I know there was some work out of NYU that was also designing a compiler built on top of Palisade. So it's definitely of interest. The Microsoft work, I think, was quite good. I believe it was coming out of the research group over there too. And like I said, I think a lot of things that are applicable there in terms of lessons learned are broadly applicable across the community of applied homomorphic encryption.
Thank you, Kurt. Okay, so
Right.
we've.
So there is another question: is it complete rewrite of Palisade or just calling Palisade C++ from JS? Yes, it is the second one. So it is just binding the original C++ library. Actually, it is building the C++ library, Palisade library with Emscripten, and then binding that binding that so that we can call it from JS or TS.
Yeah. So maybe I'll use this small pause also to maybe ask a more general question. So and this is for all speakers today. So previously Palisade was only available as basically library compiled using C++. I mean compiler, and there is some support on the Python side. What does it mean in your mind making Palisade available for WebAssembly, and for instance, what new applications it may empower, or what new maybe in, I mean, like network-oriented applications, or just like the more general picture. Why do you what motivated you to develop the WebAssembly port, and why you think it's important? And this is a question for all speakers.
I can definitely say that, I mean, aside from its applications in blockchain, I really do think that homomorphic encryption has a place on the web in general, right? A huge push has been, at least again in the blockchain community, and now I guess really everywhere, is Web 3.0. I don't know if you guys have been hearing that term thrown around, but it's the idea that, I mean, it's quite a few ideas actually that have been sort of meshed into the way we use the internet, right? And the way that we want to develop future internet infrastructure to allow this, crazy integration of, for example, blockchain-based technologies, or at the very least, cryptographically secure distributed technologies onto the web, right? And what new functionalities they may add. So I think homomorphic encryption absolutely has a place on the web. In that way, and I think that it's up to us to be able to actually make something like that happen, right? That's kind of our goal, right? Is to make sure that we can, like I said, we can prepare like a standard set of homomorphic encryption tools to be used across, and the internet in general, right? So what kinds of things do we think it can enable? I think when you combine it does really well as, in my opinion, both a primary technology and a support technology. So as a support technology, when you combine it with other technologies, you get applications in privacy that you just could not get anywhere else, right? Or it would be extremely costly from a computational point of view to do so, right? So homomorphic encryption sort of provides that cost savings and gives you additional functionality that you may not have had, right? In the event that there's no cost savings, you just can't even do that thing. Homomorphic encryption gives you that tool to be able to do that thing, whatever that functionality is, in a private way. So it's going to be in privacy, right? Establishing this level of distributed private computation across the internet, that is huge. And I think homomorphic, like I said, making sure that homomorphic encryption-based tools are positioned in the way that they're written to support these types of environments is going to be everything in the future. And that includes within blockchain-based ecosystems. So WebAssembly is one good example of that, right? Like by doing this, you can access many, many different blockchain-based languages.
Thank you, Olu. So Ted, Ismail, do you want to add anything? Okay. Yeah, I think Olu's answer was quite exhaustive. Yeah, that's it's actually quite exciting. So what you described. So let's see. Do we have any other questions left? So I don't see any open questions. So Kurt, do you have any questions on your side? And
no, I think, like I said, this is a really great talk. Especially the application and the integration. I think it's worked very well done. And I'm looking forward to seeing hopefully quite a bit more of solid, excellent work from this group.
Much appreciated. Yeah, there are quite a few ideas that have been floating around. So we welcome contributors too as well. We want more and more people to contribute ideas as well. But I think together we have a very fair shot of introducing very powerful technologies in a way that anybody can use.
Yeah, thank you.
I guess in terms of like developer accessibility, right? The NPM package bypasses both the need to run like make as a C++, which is like familiar to anybody who's a C++, but a JavaScript developer, maybe not. But it also bypasses the need to compile with Emscription, which has historically been a bit of a weird process just due to the way the versions work. So I think it'll definitely make it more accessible to users who aren't as familiar with C++ concepts.
Thank you, Ted. So let's see, there doesn't look like there are any more questions. So I think we had two great presentations today. And I mean, yeah, it's actually exciting. I'm excited at the end of these two presentations. Yeah, thank you everyone for joining us today. So thank you for great questions. And we'll see you next time, later this summer. Thank you. Bye-bye.
Much appreciated, guys.
Thank you. Take care.